Okay. Wednesday. Sarah B. Claire. Matt. Luke. Jaden. Okay, yeah. Emma. Liza. Stuart. Let's see here. Ethan. Manya. Olivia. Kashal. No, sorry. Kashal. No. Tell me your name, please. You're Kashal. Okay, yeah.
Oh, also, I don't know if you got my still for Monday or no, I wasn't able to talk.
I didn't get any stint from you. Yes, you talking about yesterday?
Oh, like Monday.
Yeah, I'm sorry, Monday. No, I didn't get it.
So should I refill it?
Remind me after class and I'll check.
Okay,
It's
cool.
possible that I somehow just spaced and missed it.
Cool.
But then yeah, let's talk after class.
Okay, cool.
Okay, Diego, Darwin, Sean, Jules, Doa, Matthew, Colin, Emily, Rennick, Sarah T, McKenna. Yes. Okay, anybody come in whose name I didn't call? Did I call everybody's name here? Okay. Okay. Okie dokie. Time to get started. Okay, so last time we finished chapter 3, and moving on now to chapter 5. I think I may have mentioned before, we're momentarily skipping chapter 4. This is just for kind of strategic purposes. In some sense, chapters 6 and 7 are the big goal of the course, and it's best, in my opinion, to get to chapter 6 and 7 as fast as possible, except for the fact that almost everything in the course is prerequisite to chapter 6 and 7. So, of course, that's why they come later in the book, right? Chapter 4, however, is not. Chapter 4 is easily movable to later, and that's why we're doing that. Okie dokie. So, chapter 5. We're going to talk about areas and volumes, how to do integrals. And the very first thing we're going to do, kind of like we did in chapter 3, is start with a point of view that's ultimately really not the best point of view, in my opinion. So now remember in chapter 3, this is related to partial derivatives. Very first derivatives we wrote down in the course, in fact, were partial derivatives. And I made the assertion that there's really a much better point of view on derivatives coming up. And we do the partial derivatives first because, well, it's kind of a nice little foot in the door, and it's whet your appetite, get one under your belt, kind of a thing. Right? And I hope y'all can, in retrospect, see that at this point that the derivative matrix is much more powerful. It's much more natural. The derivative matrix is what you do to input changes to get output changes. That's really what a derivative is. And partial derivatives are super easy to compute. They're elemental. In other words, all our other derivatives, better derivatives, are made up out of them in some sense, right? So they're great and all, but they're really not fundamentally the right point of view. So same thing's going to happen here. And so we're going to start in order to get a win under our belts. We're going to start with what is really ultimately not the right point of view on multivariable integrals. So anyway, keep that in mind. Okay, so flashback, single variable calculus, volumes of rotation, right? So suppose you have an area like that, and then you rotate that area around the x-axis, let's say, and that makes a volume, right? That makes this whole great big volume here. Okay, how would you compute that amount of volume? And the clever move, hopefully y'all have all seen this in a Calc 1 class, is to take slices, right? You take kind of slices like this, perpendicular to the x-axis. Those slices look like this here. Let's see if I can, there's a slice, right? And that slice, let's blow it up larger so we can see it better. That slice is pretty easy to talk about. It has a cross-sectional area, and it has a thickness. Let me do the thickness first. The thickness, that little width there, that is the same as, well, this little width over here on the x-axis that it corresponds to, that's your dx. Right, and then there's the question of the cross-sectional area. Cross-sectional area is, just looking at just sort of, one face, if you will. One face of that thing. Well, it's a disk. It's a garden variety geometric figure that we all know the formula for. So it's just pi times the radius squared. The radius is easily identified. I mean, so anyway, everything kind of falls into place because we know the formula for that cross-sectional area. Okay. All right, so we're going to try to, at first, take this same approach to a different problem, and I'll show you where we run into a problem, run into a difficulty. Suppose I'm not looking at a rotated volume, but just, let me change colors, a graph. And keep in mind what a graph is. Right? So graph means that the value of the function is another variable, in this case z, in this case height. Right? And that gives me then a surface. This is some surface. Suppose I want to compute the volume sitting under that surface. It's not a rotation. Now, of course, not all of it everywhere, but I want to restrict my focus to just, just the part sitting over a certain rectangle over here in the XY plane. There we go. Okay, so how would I compute that volume? And again, you can kind of, take initially the same approach of let's take slices. Here's what a slice looks like. And I got that cross-sectional area. It's not a disk. It's not a washer. It's not a square, a triangle. It's not one of these garden variety geometric figures. And so here's where in a single variable calculus class, we kind of have to throw up our hands and say, well, dead in the water. I don't know what to do with this. Okay, is everybody with me so far? So we are in a multivariable calculus class. We're going to make a different observation, and I'm going to say, well, this cross-sectional area here This, here it is, this cross-sectional area. It's not a disc and it's not, any other sort of recognizable shape, but it is, however, area under a curve. Look at that curve right there. This is literally the area under a curve. That curve is just the relevant portion of, if you look at where it came from, it's just part of this surface. Every point on that curve has z as a function of x and y. And so in fact, I can write down the equation for this curve. That curve is z equals f of x comma y, except for one little sort of asterisk. There's a temptation to say, well, that, if you have x comma y, isn't that isn't that a surface? I need this to be a curve, not a surface. Notice, however, we're looking along a slice like that. That slice means that y is the same for all of these values. Y is fixed. And if y is fixed, then in fact, what we have here is z as a function of only one actual acting, active variable, right? X is the only thing that's changing as I move across that way, right? It is x that is varying. So x is my variable there. So z is a function of, morally, it's a function of just x. And that is a curve. And we know how to compute the area under a curve, right? The area under a curve, no problem. Area under a curve is integral of that function. Now, as soon as we write this down, we get the willies, right? Because you look at that and think, oh my gosh, that's a function of two variables. Can you do a single variable integral of a function of two variables? How do you treat the y? Oh my gosh, is y a function of x? Or what do we do? Well, no, it's really not. In fact, we've already decided what to do. We're going to treat y as the constant that it is. It is literally a constant. And so this is an optical illusion. It looks like we have a function of two variables on the inside, but for what we're doing here, for computing that cross-sectional area, no, we don't. Y is a constant. Treat it like a constant, like a K or a C or something like that. Everybody with me? Okay. All right. So, I mean, that first step is really not that big a deal. I mean, so areas are integral because it's area under a curve. Calc 1, really, ultimately kind of single variable calculus, isn't it? Okay. Okay. So knowing that area here, let me zoom out for a second here. Knowing that area, clean up my mess here. Let's see here. So this area is that integral. That area is what I multiply by this thickness to get volume. What is this thickness? Well, that's keep in mind, I was slicing sort of like this to get these things. I was slicing up the y-axis. That thickness is dy. Right, so, again, looking back up to the volume question, finding that little piece of volume dv. Let's see, let me make a color choice here. Let's use green here. This piece of volume dv is, it's cross-sectional area times dy. Cross-sectional area we already computed. It's that yellow integral. And plugging in then, we get that. Okay, so again, area times dy. Is everybody on board? Yes.
So if we were to compute this, we want y to be fixed.
Well, while we're computing, so you got a great question. I am going to get to that, but I mean, while we're computing this integral, this dx integral, yeah, absolutely, y is fixed. But well, yeah, that's right. I mean, after you're done computing, I mean, effectively what you're computing is that cross-sectional area as a function of y, right? But while you're computing it, that computation goes down as, all right, you're going to give me a y, right? I mean, it's for a given value of y that you want to know the cross-sectional area. So you give me the y, and now we're going to treat y as being fixed. And, for that fixed value of y, we compute the cross-sectional area. And of course, that computation applies no matter what value of y it was. Yeah. I saw another hand somewhere. Anybody? Okay. So, yeah, so that's my DV. And if I want to compute the grand total, if I want to compute the grand total volume, this whole thing, then I'm just going to add up all those little DVs like so. These here, of course, being the DVs. All right, so I mean, it's a little weird, but this nevertheless works just fine, right? If you just kind of push through, then sure enough, everything works. So let's see here. Yeah, so terminology, this thing that we've ended up with, I guess, why don't I zoom back in? This is called an iterated integral. It's the very common terminology. This has always kind of bugged me a little bit because to me, an iteration means that you're repeating something, right? And presumably that you're repeating the same process. It's not really quite what this is if you really look carefully, right? First, we're doing an x integral over a range of values of x. And then subsequently, we're doing, to me, a pretty different thing. We're doing this y integral. It's not the same thing, over a different range of values. It's the range of values of y. So anyway, to me, the term iterated integral doesn't quite hit the mark. I would prefer if the terminology had been nested integral, because it's literally, no kidding, an integral inside of an integral, right? So to me, it's nested as the, anyway. Far more common terminology is iterated integral. So anyway, it is what it is. Okay. All right, so now a little bit of terminology I want to warn y'all about. Keep in mind in this process, we first kind of did our y slices first, and then, y goes from C to D. So there is an argument that says that our y integral is really kind of the first integral because, again, in the slicing process, it was first. And then we subsequently did an x integral for the purpose of computing that cross-sectional area. So arguably that one is second. So there's going to be a temptation to call one of these the first integral and the other one the second integral. Problem is that when it comes time to computing the integral, well, guess what? You kind of have to do this integral first for computational purposes, because we don't even know yet what the integrand is for the dy integral. Right? The integrand for the dy integral is the dx integral I haven't computed yet. So you have to do, from a computational standpoint, that one first, and then the dy integral second. So ultimately, I think this terminology of first and second is just unclear. And I urge you not to use or even think about these integrals in those terms. What I think is perfectly clear is inside versus outside. And as you slice what you might call outside in. And then when you compute inside out. Sure. Right. But no one will ever misunderstand what you mean by the inside integral. All right, and then last sort of reminder before we go on, for this inside integral, right? Don't forget that we're going to treat the outside variable as being constant. And of course it is, because that's what we're doing while we compute that inside integral. That inside integral is for the purpose of computing this cross-sectional area. Cross-sectional area for a certain value of y, which is fixed. Okay, so something to keep in mind, the integral to the outside is constant for the inside integral. Okie dokie. So let's see an example in action. We want to compute the volume under a graph. So again, that's what our formula does, right? Graph, because we have we're going to set z equal to that. And over a given rectangle. Oh, let me talk about the terminology. The notation here. This notation we haven't used before. This is just a shorthand notation to represent a rectangle. The first part of what's given here represents the range of values of x for the rectangle in question. The second part of it tells you the range of values of y for that rectangle. This notation of interval cross interval, that is just a shorthand notation that says, yeah, I want to talk about the rectangle whose, if you will, sort of projections to the x and y axes are as given there. Is everybody good with that? It's just notation. Okay, so good news. We don't have to go through a slicing argument again. We already did that, right? Volume under a graph, yeah, boom, iterated integral, right? The function whose graph you're looking at is what goes on the inside. And so we can just go straight to the computation part of this problem. So let's see here. We have this, let's see here, dx integral on the inside. Couple of little tricky curves. You want to make sure not to step on these little landmines. Don't forget, while you're doing that inside integral, the variable to the outside is constant. Y is a constant. That means that, for example, also y squared, constant. You're going to have this urge, right? This compulsion to, oh, I'm doing an integral of y squared. Shouldn't that be 1/3 y cubed, right? Almost reflexive to want to like apply the rules, right? But you got to keep in mind, no, x is the variable. That's what you do for functions of x, expressions that have x's in them. Y is a constant, treat it like a constant. And so notice, color. The antiderivative, the x antiderivative of y squared is x times y squared. So this is good news. Right? It's kind of like with partial derivatives. You get to treat other variables as constants. Isn't that nice? In fact, this is sometimes called a partial integral. That inside integral is a partial integral. So treat the variables as constants because they are. And just, the hardest part about it is remembering to do that. Okay. All right. Of course, the antiderivative of x squared with respect to x is 1/3 x cubed. And then you put your bounds in. Now here's another potential landmine. These numbers go here, and a lot of people will just write down 0 and 1 and off they go. And the slight risk is that that's all you write down, just the 0 and the 1, because after all, those are what you do. If you don't write down a reminder that tells you what those variables are plugging in for, you'd be surprised how easy it is to accidentally take this 0 and not only plug it in for the x's, but also to maybe accidentally plug it in for the y too. Surprisingly easy to do, right? Which of course is wrong. We don't want to do that. So I'm a big believer in don't just recopy the numbers as we would for a single variable integral. Indicate specifically in your notation that these are values you're plugging in for well, which variable? Well, for x here, right? And so these values go here and here. When they don't plug in for y, well, of course not. Y is a constant. It's just y. It just sits there. Everybody happy? All right. And it's all algebra from there. You got to be careful. You plug in and you get another expression, but then you do have another integral left to do. This one is literally a single variable integral. Function of y, dy, nothing to it. Antiderivative, plug in the values, do some arithmetic. I hope I got that right. And there it is. Okay. All righty. Now I'm going to make a suggested exercise for y'all, which is to go through this slicing process, except slice it the other way. Instead of taking, again, what you might call y slices first, because instead of slicing first perpendicular to the y-axis, like we did here, and then noting that that's an area under a curve, blah, 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 try instead doing your first slicings perpendicular to the x-axis. Your cross sections are going to be kind of like this. Right, and think about what's the width and what's that area? Well, the area there is an area under a curve. That curve, what's a constant? What's a variable? A lot of little things are going to change. It's going to be structurally just like this, but the roles that the variables are playing are going to be different. Right, I think it's a really nice exercise to look through, make sure you understand this argument. Apply the same ideas, but reversed to doing it this way instead. And what you will come up with, what you should come up with, is that there. This being now a second computation of the same volume that we already computed. Keep in mind, we already computed the volume sort of slicing the first way. So we now have two different formulas for computing the volume. And one point of view you can take on this is that it's like we kind of did this with the bounds and the differentials. This little move right here, right? And but warning, this only works when the domain is a rectangle. So it's because of the fact that we have a rectangular base that this works. And we're going to consider soon non-rectangular domains. Things do change when that happens. And in particular, this little move right here of, you can switch the order of integrals by just doing this. Yeah, that goes away. It doesn't happen. But for a rectangle, very convenient. The y bounds over here are just the outside differential and bounds just become the inside differential and bounds. And then the inside differential and bounds become the outside differential and bounds. It's kind of nice that for rectangles, it works out really simply. All right, is that cool? Okay. So let me remind you other things that we've done with single variable calculus. We computed, for example, the mass of a rod of non-constant density. This is a classic single variable calculus problem. And you do it by basically it's just an integral of the density. I mean, for computing volume, do an integral of height. To compute mass, you do an integral of density instead. So, well, cool. We've got a kind of a two-dimensional version now of a volume argument. Can't we just do the same thing to compute a two-dimensional mass? What if I had, in other words, if I want to compute the mass of a rectangular sheet, right? Nice. So a two-dimensional distribution of area, where I have density given. Now, heads up, do be aware, when you have density over a two-dimensional region, density now means mass per unit area. It's no longer mass per unit length, because we're not measuring little pieces of length. We're looking at little pieces of area, and mass per unit area times area is what gives you mass. Okay, does everybody see the question? And here's the bad news. Our argument is going to kind of crash and burn. And so what I want to do is put these arguments sort of side by side. Up here, we have the volume argument that we've already made, and that works just fine. And then down here is the candidate. This is if we were to just kind of copycat and with our fingers crossed and hope that this makes sense, what we would kind of sort of want to write down. And I claim it doesn't work because of the following. Let's think through this argument first. Cross-sectional area comes about because we already knew that this was height, and we're multiplying a height times a length, and height times length gives me little pieces of, I should really do it like this, little pieces of area. And I know what area is, right? I understand area. I've spent a lot of time playing around with areas. And if I have an area here and an area there, and then a bunch of little pieces of area, it's very persuasive for me to say, look, if you just add up all these areas, you get the area of the whole thing. Sure. Okay, all right. Well, here's what happens if I try to do that down here. Okay, so this is mass per unit area, okie dokie. And then I'm going to take that, and apparently the first thing I'm going to do is I'm going to multiply by dx, which is a length. And wait a second, what do you get when you multiply mass per unit area times length? And that's not right. That's a mismatch. It's a problem of, you could say it's a units problem, but it's really not. All right, it's not a matter of, oh, I wish we were in metric. Right? It's this isn't a thing problem. Right? Now you could say, I mean, just from a units point of view, you could say, well, it's mass per unit length, I guess. But in a situation where mass is distributed across areas, I don't know what mass per unit length means. It's not something I have a previous experience and familiarity with. So is this something that I can then subsequently say, okay, well, let's add this thing that I don't even know what it means. I'm just going to add up a bunch of them, because let's face it, when you add up a bunch of things, you get that applies to the total or something, right? We don't even know what we're talking about. So the argument crashes and burns here. Now, why did it not crash and burn in the initial example? And ultimately, it's because geometry is just something we're ridiculously familiar with. We have a pre-existing notion called area that we understand. We understand the connection between area and height and length. We understand pre-existing the relationship between area and volume. We got lucky. We just happened to have this pre-existing concept that was exactly what we needed to go along the way. And in all other contexts, other than the peculiarly convenient and familiar context of geometry, other than that, it just doesn't really quite work. Okay, now I want to recognize that, yeah, sure, you could make it work. I can make an argument about what this thing is, and I could develop some intuition for it and make this argument, cram it through, right? But it's a lot of effort, and furthermore, it's effort that you would have to reproduce every single time you want to compute something other than volume. So maybe instead of mass, you want to compute work, or maybe you want to compute a probability, or maybe you want to compute economic surplus, or maybe you want to, oh my gosh, right? There's so many different, every single one of these times you're going to have to re-engineer a new concept that you have to make sense out of it. This is not the way to do it. Okay. All right, so I want to emphasize this iterated integral argument as an argument for computing something only makes sense for volume. All right. Okay, moving along. Okay, so let's try to figure out our way around that that impediment. I'm going to define something called a double integral. I'm going to build up to it. I want to remind y'all first what a single variable integral is. So a single variable integral is a Riemann sum. Here's the formula for a Riemann sum. And I'm sure y'all have seen this before. Riemann sums tend to get a sort of a gloss over treatment in single variable calculus classes because after all, computationally, who needs it, right? Riemann sums are nowhere near as convenient for computing stuff, for computing, integrals, that is, than the fundamental theorem. Fundamental theorem is way better, way easier computationally. Yep. And so this tends to get glossed over and ignored because high school calculus classes tend to be about computing stuff, right? So, well, here's an unappreciated point, and that is that that's not what Riemann sums are for. Riemann sums are not intended to be something that's computationally convenient, to brute force compute a Riemann sum. Riemann sums are intended to be things that connect. It's an expression that connects to applications. And again, just for the record, I want to it also serves some abstract sort of rigor, mathematical purposes. But I know I'm not going to have a big appeal among non-math majors here. But anyway, so for our purposes, what Riemann sums are really important for is that they're what these various applications connect to. So, for example, if you want to compute the mass of a rod, how do you argue that you can write that down as an integral? Well, you take that mass, you chop it up into little pieces, and you talk about, well, each little piece I can multiply density times length, and you are in fact writing down a Riemann sum. You might be writing it down using integral notation, but ultimately deep down underneath it all, what you're writing down is a Riemann sum. Okay. So Riemann sums are super important for that reason. Now, a lot of people think, you know what, I'm gonna view it as an area under a curve instead of a Riemann sum, and I don't need to make a Riemann sum argument. And I say, well, no, you actually do, because when you've been asked to compute the mass of a rod, one-dimensional rod, right? The rod, it starts here, it ends here, it's entirely along the x-axis. Where's the area? There's no area, right? I claim there is no legitimate argument that I've ever seen that directly computes mass to area under a curve. Directly, that is. Now you can, of course, make that connection, but the way you do it is you argue that the mass is computed with a Riemann sum, and that Riemann sum can be thought of as the same one that computes an area under a curve. So the only way to even bring area into the question in the first place is by way of Riemann sums. So ultimately, when you get right down to it, this idea of thinking of integrals as areas, area is pretty removable from that story. You don't really need it. You could cross that off, pretend you never understood integrals as being areas at all, and it doesn't really affect the functioning of applications. You write mass as a Riemann sum. You compute that Riemann sum, which is the definition of an integral with the fundamental theorem, and you spike the football. No area needed. Okay, so anyway, this is one of my little pet peeve soapbox topics, and I have a longer rant on this. If you're curious, if some of this is making you a little bit worried, oh my gosh, I really thought integrals were areas. What else don't I know about integrals? If you're a little worried about that, which is a reasonable position. I have a long 30-minute discussion of this on my YouTube channel, Miscellaneous Topics playlist, where I have all my sort of extra, recordings. And it's just called, what is an integral? I think is the title of the thing. Give that a look and you'll hear me much greater length talking about this. Okay, so back to, again, what an integral is. An integral is a Riemann sum. Sometimes, in other words, we need to take intervals. We need to chop up those intervals into little pieces. We need to do little calculations on each individual little piece, and then we need to add up those individual calculations. Okay, so a bunch of little pieces. We do calculations on each individual piece, and then we add up those calculations and take a limit to make round off errors go away. Okay. What we want to do now is figure out how to do a two-dimensional version of that. Right. So, you know, maybe you think of, you know, here we're trying to compute the mass of a rod. Again, let's try to avoid the area metaphor because it's can be misleading and it's you know, peculiarity in some sense. If you want to compute mass of a rod, well, we chop it up into little pieces. And then we do, you know, and add it up with a Riemann sum. So a two-dimensional version of that, I argue, would look something like this. Here's my rectangle, and I'm, excuse me, I'm now going to chop up this rectangle as follows. I'm going to, I'm trying to hit these points here. I'm going to slice that way, and then I'm going to recognize that these, you know, these are still kind of too big, and so I'm going to slice it again. And now I've sliced it up into little bitty pieces. And there's a bunch of details to be worked out. We'll get to the details in just a second, but big picture, the idea is on each one of these little pieces. So for example, on let's say that piece right there, on that little piece, I've got a little tiny little piece of area. Maybe I know on that piece what you know, what the mass per unit area is on that piece of area. And if I know mass per unit area, I could multiply by area and I get mass, something I understand, right? A thing that's real, and then I can make simple arguments about. Right? Okay, so the area that I would want to multiply by, well, in this case, mass per unit area, but it would be something different if you're computing a different thing. We'll worry about the different applications later. And that will compute for me the mass on each little piece. And what's the total mass? Oh, well, the total mass, we'll just add it up. You just add up over all those pieces and you get the total. Yes?
Why do you multiply delta x, delta y?
Yeah. Okay, because that is the area that I'm interested in. So keep in mind, the big strategy here is that I want to compute this, you know, the size of this little piece here is area. Its area is, well, let's see here. It's what you might call its width, which is delta x, right? And I want to multiply that by its height, which is delta y. I mean, it's a different expression, but width times height gives me that area.
Then why do we need f like xi yj?
Yeah, well, so right, so keep in mind, whenever you do an integral on each little piece, you need to know the size of that piece, but the size is not what you're actually interested in. What you want to compute is some other quantity, right? Like mass, right? So over here in the two-dimension, in the single variable version, if I'm computing mass, length is just a means to an end. Length is what I multiply times mass per unit length to get what I actually care about, which is mass. right? So likewise over here, area is part of the story, but I'm actually interested in mass, and area times mass per unit length. Sorry. Area times mass per unit area is what gives me mass. Yeah. Everybody good? Okay. All righty. Yeah, so the details I'm going to largely kind of wave my fingers at because as we slice the area, notice we are also slicing up the x-axis, and we know what happens when you slice up the x-axis. There's a delta x, there's an x sub I, and that's the same. We've already, there it is. We've already, documented the little details of how what happens when you slice up the interval from A to B on the x-axis. So I'm just going to observe then that, okay, well, the next thing we do is we slice horizontally. And now notice that as I slice horizontally, I am in fact just slicing up the y-axis. It's not from A to B, it's from C to D. But it's still an interval that's being sliced. And so, different details, but strategically the same. Instead of B minus A over N, it's D minus C over N, etc. Other little highly analogous, appropriately different details. Yes?
Could we write that as an integral as well?
Oh, we're about to write it as an integral. Yeah. Yeah, exactly. So ever so slightly ahead of me. Before we go on to that, is everybody good with this? And I don't want y'all to get bogged down in the micro details of exactly what are the formulas here, because it's not really, the point is that in the same way that we can chop up an interval, we can kind of double chop a rectangle. Okay. So yeah, so as you predicted, this Riemann sum, and by the way, let me come up here. This Riemann single variable Riemann sum that we see connects to so many different things, right? Wow, this is a useful construction, this Riemann sum. Let's call it an integral. And we're gonna do the exact same thing down here. This expression, it's going to allow us to answer just a ton of questions. There's just going to be so many different situations where I'll have a rectangle that I'll want to chop up into little pieces, for which I'll want to multiply the area times something for some reason, maybe mass per unit area, so I get mass. Maybe population per unit area, so I get population, right? Maybe this is Wyoming and I want to compute the population of Wyoming, right? Or any number of other possible applications to get some accumulating quantity that I then add up over the whole, right? So lots of such situations, and in anticipation of that, we define an integral. This is called a double integral. This expression that we have on the previous page there. It's called a double integral. Yeah. Okay. Yes.
So because we have it as a rectangle, is it the same case as we were saying before, where it only works for volume?
Oh, well, no. So that's the beautiful thing about this. This works. This does not rely on the sort of intermediate notion of knowing what the cross section looks like, right? So when I argue here that a formula like this will allow me to compute mass, I'm not making any arguments about what happens if I multiply mass per unit area times just a length. That doesn't come up in this argument. What I'm directly doing is computing this area, the whole area. It is an area, and yeah, mass per unit area times area, no problem.
So taking one of these is different from.
Absolutely. This is a very different construction. Yeah. So by the way, some of y'all may have seen some multivariable calculus in high school, and it's commonly stated that double integrals and iterated integrals are the same thing. Oh, this is wildly wrong. There are a very large number of cases in which they are equal to each other, that's not the same as saying that they're the same thing. They're very importantly different constructions that as constructions have different desirable characteristics that happen to always give you the same value, but they are very different as constructions. Yeah, so does that make sense? Yeah. Okay, so double integral. Just about the notation, where does this notation come from? Well, you could kind of see area is height times width, kind of, I mean, it's pretty plausible, right? dA representing a little piece of area, because that's what the delta x delta y is. By the way, with that in mind, sometimes this is actually written as dx dy, and I think that makes it look too much like an iterated integral. So all else being equal, I think it's in most cases suboptimal. But anyway, you could write that as dx dy. I'm going to write it, however, as dA. And then the summation. This is a limit. Oh gosh, this is a limit of a sum. But notice it's a sum in two different directions. The I that controls where I am, sort of, how many spots have I moved along in the X direction, is independent of the J that's telling you in some sense how far you are sort of up and down. So this is a summation in two different directions, and thus two integral symbols over here. Okay, now I'm going to emphasize here. There's some stuff in the book that is beyond what we need to deal with in this course. So y'all are absolved of responsibility of the book's presentation where they use what are called irregular partitions. That's where they chop it up, but they don't make all the pieces the same size. When you're dealing with a more sophisticated version of what we're doing here, that's important. Likewise, instead of always evaluating at the corner, they argue that, well, you could take actually any point at all inside of your little piece of area, and so that's called a test point. Here, sometimes it's called the sample point. Anyway, whatever, and that matters in much more sophisticated situations than what we're going to deal with in this course. Since we're not going to deal with any of that, I don't see any point in including in the definition stuff that will not make any difference for us. We're only going to deal with continuous functions, possibly piecewise continuous. But anyway, in any of the cases we're going to deal with in this class, these make no difference at all. They're very important if you take a class in analysis. If you have wildly discontinuous functions, really much more sophisticated stuff, here it makes no difference at all. Okay, so just ignore all that stuff about irregular partitions and test points. Okay, and so just as a first example, since we've basically already done it, let's reconsider the question of computing the volume under a graph. The graph, of course, being this surface. I've already done this by slicing up slices. We've got an iterated integral, but check out the much easier argument I could make, which is, yeah, well, let's just look at little pieces of area down here in the domain, and let's multiply those areas times, well, let's see, whatever the height is here. What is the height? Well, the height is z, which is the value of the function f. So looking at the picture, base times height, I can compute the volume of that French fry with this little formula right here. Right, the volume of the single French fry, you can represent with this expression. You just add up to get the volume of the the jumbo fries here. Add up over all those pieces to compute the total volume. Now, how do I compute this computationally? Where's the fundamental theorem of calculus kick in? Oh yeah, that's separate, right? But just making the connection between volume and a double integral is kind of a snap. Very convenient. Okay. All right, now I'm out of time, so I'll pick up here next time and see y'all later. Let's see, where am I? I'm on page 5. Okay, all right. Yeah, see y'all later. Have a good Wednesday, and office hours in a couple minutes, of course.